Hello, so we continue here with our discussion, and in this module we try to evaluate the output response of this circuit, where we see to the inverting input we have a resistor connected, and from inverting input back to the output here we have a capacitor, and the non-inverting terminal is grounded. So the current due to applied signal that flows through the resistor is I, and the node voltage at the inverting and non-inverting terminals are indicated by V1 and V2. The current that flows through the capacitor is IF, and we know that there is no current trying to flow in the operational amplifier. The operational amplifier has a gain indicated by A. So what we do here is we apply Ohm's law. So we can write Vi minus 0 divided by R, that is the voltage drop across the resistor R, divided by the value of this resistor, that is current I, and that is equal to the current flowing through the feedback capacitor, 0 minus Vf 0 minus Vo divided by Rf. Not RF, we have impedance here, capacitance impedance, that is indicated by Z. So what we see here, we have in the S domain, we write Vi of S divided by R, that is equal to minus Vo by Z of S, which can be written as 1 over Cs. Okay, and we know that Z of S is the impedance of a capacitor, which is 1 over Cs. So we can further simplify this expression, Vo of S divided by Vo of S, that is the output voltage divided by input voltage, that is minus 1 divided by RCS. We just do the simple manipulation, take the ratio of voltages and 1 by RCS. So we put S equal to Z omega, J omega in this equation, and what we see, the expression becomes like this. Okay, and here we define one more term, omega C, that is equal to 1 over RC. This is called as a cutoff frequency or break frequency of filter, because we are going to see that this circuit behaves as a low pass filter, or in other words, it is called as integrator. So we simplify this expression with this equation right over here can be written as RC is 1 by omega C, so it is like this. We just replace the RC, that is equal to 1 over omega C. And now we are trying to obtain the magnitude and the phase plot of this transfer function. So this is a transfer function which is given by this final expression. So we see that the magnitude can be written as simply we in the numerator we have -1. So we have imaginary part is 0. So we can write -1 square plus imaginary part is 0, right? So, and in the denominator we have real part 0 plus imaginary part is square. So it is simply 1 over omega by omega c, which is final form is like this. What about the phase? That is an angle. We know that what is the expression right here? We are talking about the expression here, this one. So angle is the angle of numerator minus the angle of denominator. So it's a -1. So if we look at this diagram here, this is called as real axis. This is imaginary axis. It is the diagram of S-plane. Okay, and we have this minus imaginary axis. This is minus real part. So in the numerator we have -1. So -1 is 0 over here. Somewhere here is the -1. So we say that that's the 0. And what is the phase about that? So we start, for the phase we start like this. So this is 0 degree. This is plus 90 degree. This is 180 degree. This is 270 degree. And this is back to 360 or 0 degree. So the phase we start from this one, right? That is our phi or phi. So we can write phase of the numerator, which is 180 degree, and the phase of the denominator, which is the tangent inverse of imaginary part divided by the real part. Real part is 0 here, right here in this expression, right? So what we see here, this could be written as 180 degree minus tan inverse. Anything divided by 0 is infinite. So we see that this takes the form of 90 degree. So phase is always 90 degree. Okay, so now we can, there is another way to solve the phase. So we see that we can write that here we have this term V of j omega divided by V of j omega. And that expression that we have here is -1 over j omega rc, right? Is basically this equation -1 over j omega rc or omega by omega c. So what we see here, we can write it is here in this way, which would be -1 divided by j is minus j into 1 by omega rc. So this is j 1 by omega rc, which is nothing but j by omega rc. And then the phi or the phase here would be tan inverse 1 over 0, which is the phase of the numerator, where here the real part is 0 and imaginary part is 1. So that's the phase of the numerator minus tan inverse. Here the real part is there, but the imaginary part is 0. So 0 divided by omega rc. We see here that's your 90 degree minus this is 0. So again, this is 90 degree. So we see that there are two ways. One is this one or one is this one. So this is how we got the phase here. Okay, so coming back to our expression, we see here now, we try to obtain the plot. So first condition at omega is equal to 0, we have to get the expression for the magnitude and the phase. So it would be, what is the expression for the phase? phase is, sorry, the magnitude is omega c over omega. So this is omega c over omega, which is now going to be infinite. So we see here at zero frequency, the magnitude response is infinite. Okay, and what about the phase? Phase, uh, which is the angle, we've seen that, that is 90 degree at all frequencies. So from here we see that, or from here, okay, at omega is equal to omega c, which is the cutoff frequency. Let's try to obtain the value for the magnitude, which would be omega c divided by omega c. So that's nothing but 1. And again, the angle is 90 degree right here, right here. And at omega is equal to infinite, we see that this magnitude takes the form of 0, and the angle is 90 degree. So how to obtain the plot here? So we see that the plot can be obtained like this. So let's say we have this point omega is equal to 0. Here we have magnitude A at omega is a very large gain. So we say that is infinite, right? At this point here. At omega is equal to omega c, somewhere, let's say here, omega is equal to omega c. What we have the value to be equal to 1. That is, let's say it's value is equal to 1, excuse me. And what about when omega tries to approach infinite? So it goes to 0. So somewhere here we say that this value goes to 0. Okay, so that's the magnitude plot that looks like. So we don't need to draw this line basically. We don't want this line actually. Yeah, so it looks like this. And at this frequency, you see that. But what about the phase? That is the angle phase. P is always having the value for all frequency to be minus 90. This is a plus 90 actually. That's all.